So this is a particular circuit diagram. Let me also pick my pointer. So this is the overall subsystem diagram here at a block level. So I have the latch 1 here, latch 2 here, and in between the combinatorial circuit number 1, followed by the combinatorial circuit number 2, which is there in between the latch 2 and latch 3. Right, so in this case, what we are saying is the combinatorial circuit 1 can actually borrow the time from the second clock high level, and the maximum borrowing time is nothing but the TC by 2. So TC by 2 represents. So if this is TC by 2 and this is TC by 2, making one particular clock cycle, so I'm going to write it as TC. And so it can borrow or it can extend the combinatorial circuit output can extend till we have the setup time associated with the latch 2, right? So it can extend up till this particular portion of the time. And so the maximum borrowing time turns out to be nothing but TC by 2 minus this T non-overlap, right, and the minus of T setup time, right? So this is what in the timing diagram I have drawn here. The D1 is the signal at the input of the latch 1. The output of the latch 1 will be coming out after the TPDQ, and then D2 signal, which is the output of the combinatorial circuit number 1, will come at after the TPD1. So the TPD, the propagation delay of the combinatorial circuit number 1, and the latch output, the second latch output will come after the TPDQ2, and then the combinatorial circuit number 2 is going to come out after the propagation delay of the combinatorial circuit number 2. Right, in this whole sequence of the output that is being generated after the every blocks. So this one, the combinatorial circuit number 1, which is supposed to operate in this particular, supposed to operate and then make the signal available in this particular region of the time, or in this particular region of the time. And because it is supplying, the combinatorial circuit number 2 is supplying the output as an input to the latch number 2. The latch number 2 can actually capture till it reaches the T setup time with respect to the clock going low, right? So it can extend, the combinatorial circuit can actually extend or borrow the maximum time of TC by 2 minus of T setup plus T non-overlap, right? Hope this is clear. Now, just to take an example of the time borrowing, let's see this particular subsystem level diagram. So we have the latch 1 here and then latch 2 here, and in between there is an adder block which is taking around 590 picoseconds of the propagation delay. Right, it's kind of very, very heavy considering the 3 blocks here, mux 1, mux 2, mux 3, which is taking around 60 picoseconds of propagation delay, 80 picoseconds, and then 70 picoseconds of the propagation delay. The other delays that has been mentioned here is 100 picoseconds, 35 picoseconds, 55 and 45 picoseconds are nothing but the contamination delays. Right, there's another path here for coming from mux 4, mux 2 and mux 3, and which the mux 4 has is characterized with a propagation delay of 110 picoseconds and 95 picoseconds. Right, all right, so with this particular parameters and then with the latch parameters, which is characterized to T setup time of 40 picoseconds, hold time of 5 picoseconds, PCQ of 82, PDQ of 82 picoseconds, and then the contamination clock to Q is also given. One needs to find out what is the minimum clock time period, and that is something we can easily find. So looking at the timing diagram, we can say that the TC, the minimum TC should be nothing but greater than or equal to TPDQ1 plus TPD1 plus TPDQ2 plus TPD2. So in that sense, TPD, so I'm assuming that the L2, L3 and the L1 and L2 latches have the same characteristics. So I'll use the TPDQ1 and TPDQ2 parameters to be the same, right? So both the latches has the same parameters, which is given here. So I will use 82 and 82, and then in between the propagation delay of adder is 590 picoseconds, and then the propagation delay of these 3 blocks will be 60 plus 80 plus 70 turns out to be 210. So this is 210 and this is 590. So if I add for all these 4 components, I'll get 964. So I can as well have the minimum clock time period as 964 picoseconds. Right, so that is our clock time period that will design for this particular subsystem block. If the clock time period, if I choose to be 964 picoseconds, then now the half the clock time period turns out to be 482 picoseconds. And it's kind of very important to use this TC by 2 to understand how much of the maximum borrowing time is available for the adder circuit, right? Because that is the combinatorial circuit number 1. And if I actually see this, the adder circuit has 590 picoseconds, whereas the MUX1, MUX2 and MUX3 put together has, if I actually round it off and then make a cumulative assessment, it will be 60 plus 80 plus 70, turns out to be 210 picoseconds. Right, so 590 is much higher than the 210 picoseconds. So in fact, what is likely to happen is the adder circuit is occupying more time, or rather it is entering into the phi 2 clock being high. It is utilizing some part of that, right? And then I think the L2 is kind of getting captured, and then it is the input is supplied to the MUX1, MUX2 and MUX3. Right, so the adder block is actually extending beyond the first level of the phi 1 clock, and then how much it is extending. So from among this 590, we know that 482 picoseconds is only the level high which is there. 482 picoseconds is is the clock level high here. But the adder is going to take more than 482 picoseconds, and then we need to understand how much of time it is kind of borrowing. Right, so if I draw the timing diagram here of phi 1 signal and then the phi 2 signal, and then we know that from here to here it is TC by 2, and then from here to here it is TC by 2. Right, so this will be TC by 2 and TC by 2. Right, so TC by 2 is nothing but 480, whatever we have calculated, 482 picoseconds. So that is what the value is. Now, if I draw the timing diagram of D1 signal, Q1 signal and D2 signal, D2 here, this is very interesting. It takes 590 picoseconds, and then it is made available into, in this phi 2 being high. Right, so this after 590 picoseconds, the D2 signal is now available in this clock level being high. So the first half cycle is what is written as 482 picoseconds. Hence the latch 1 and the adder latch 1, which is taking, it generates the output after 82 picoseconds, and the adder generates the output after 590 picoseconds. So what it is saying is the latch 1 and the adder borrows 590 plus 82 minus 482, which is around 190 picoseconds. Right, so it extends 82 plus 590, it is more than 482 picoseconds. So it extends beyond 482 picoseconds, and how much time it is borrowing? It is borrowing around 190 picoseconds. Whereas the maximum borrow time that has been available is nothing but 482 picoseconds minus the T non-overlap minus the T setup. Right, so that will be 482 minus the T setup is 40 picoseconds minus the T non-overlap. Here the non-overlap is not at all characterized, so we will assume it to be 0. So the maximum borrowing time it has is 442 picoseconds, out of which it is actually borrowing 190 picoseconds. So it is very well, it is very well placed. All right. And then once it reaches, after the 590 picoseconds here, and then we will have one more 82 picoseconds because of the latch 2 design. The latch 2 output, the propagation delay of D2Q will take some time. That will be 82 picoseconds, and after that we will have 60 plus 80 plus 70, which will be 210 picoseconds. So overall, it will get captured again somewhere at this particular portion where it had started. Right, so that's how we are actually designing the clock time period. Right, hope this is clear. So the borrowing here, it is actually borrowing 190 picoseconds. So let's continue with a new module called as clock skewing. Again, a very important topic in the subsystem design. and of course the analysis of the subsystem design. So let me draw the chip level 2D diagram. So let's say that we have a chip here, and I'm going to put my clock circuit. So I'm going to say that, okay, the clock circuit is somewhere here. So what it means is this is going to generate the clocks. So this is going to generate the clock signal here. And generally we will have minimum number of clocks. We either have 2 or 3 clock generating circuits in the whole chip. And let's say that we have our sequential elements and then followed by the combinatorial circuits. So let's say that we have this flop designs here. I'll say that this is a flop 1, and then we'll say that the flop 2 is here, and we'll say that the flop 3 is here. We actually don't know where are the flops going to be placed in the whole footprint of the chip. And the reason is very simple. We actually design the blocks, the subsystem blocks, and then and then it is being submitted to the placement and routing designers. So they actually tend to place these flops as well as the combinatorial circuits in between them. So we will also have a combinatorial circuits in between. Combinatorial circuit here, number 1, combinatorial circuit number 2, or wherever. And that the placement and routing designers will then place these flops and then the combinatorial circuits such that it will optimize the area, it will optimize the power and other things. Right. So in that sense, what we don't have is the placement of the flops designs and then the placement of these combinatorial circuit blocks. But what we know is we know the flow. We know the flow of flop 1 goes to the flop 2 via the combinatorial circuit, some particular combinatorial circuit number 1 or 2, and then flop 2 will go to the flop 3 and via the other combinatorial circuits. Right. So in that sense. In that sense, we know how the flow is, but we don't know the placement of these flops. Right. And remember that the clock signal, we generally have minimum number of clocks. What it means is a clock circuit or a generating circuit is then distributed to the different sequential elements. So we have this particular clock segments, which is going and connecting to the flop 1. It is also connecting to the flop number 2, and it is also connecting to the flop number 3. Right. Notice here that the flop 3 has the maximum interconnects here. Flop 1, or rather flop 2, has the minimum interconnect length here, and flop 1 has the in between the interconnect length here. So what it means is, even though the clock is generated here, by the time it reaches the flop 1, it will be delayed. By the time it reaches flop 2, it will be delayed, and by the time it reaches flop 3, it will be maximally delayed. Right. So if the clock is generating this signal, right, and by the time it reaches flop 2, there may be a slight delay. Right. So I'll write that the delay will be delta 1 for the flop 2. Here flop 1, there will be a slight delay again. And then I'm going to write it as delta 2. And in the flop 3, it will be the maximum delay. So I'll write it as delta 3. And notice that the delta 3 is actually very, very large compared to delta 2 compared to delta 1. And if actually I don't know the placements of flop 1, 2, and 3, in fact, it could be completely the other way also. Flop 3 can be very, very close to the clock. Flop 1 can be very, very far away from the clock. Right. And while I'm actually designing, at a stage before the routing and the placement, what we really want to do is, irrespective of the flops placement, we have to ensure that, even if I have a delayed clock, even if I have a skewed clock, right? Even if I have a skewed clock, then also the circuit should be able to capture the output. Then also the flop designs, or whatever, the sequential element designs, it could be a flop, it could be a latch, it could be a pulse latch, it should be able to capture the input at that particular skewed clock. right? So if we are expecting that it should be captured in the second clock, it should be able to capture that, right? So in that sense, what we are saying is this delayed clock signal, also called as skewed clock or the clock skewing, and we should design the circuit in a way that it should be resilient to this particular skewed clock, right? So moving ahead, let's take a simple example of what you used to do. Let's say we have the, let me draw it here. So we have flop number 1 connected to the combinatorial circuit, and then that goes to the flop number 2. And then we have the clock which is kind of generated. Right, remember that flop number 1 has a delayed clock, flop number 2 also has a delayed clock, or it could be it could be very near to the clock. So what do we do? So if we have the clock characteristics of the clock over the chip design, and that is something we can actually get it characterized by the clock designers. So if I know the chip design area and then where the clock is going to be placed, and then as a designers, I need to know, I already have the characteristics of the clock. I will have the clock with no delay, and we can easily get the clock with the maximum delay. So basically I'm saying that the clock characteristics or the clock skewness, the maximum skewness for a particular chip, right, we will be able to know from the clock designers. And if that is provided, then I can ensure that, consider the worst case, right? Consider the worst case and then try to design the combinatorial circuits, TPD or TCD parameters, right? So what we are saying is we have to consider the worst case of the clock skewness, right? And then design our combinatorial circuit. Right, so in this particular sequence of F1 and then the flop 1 going to the combinatorial circuit number 1 and then going to the flop number 2. So this is the clock signal, and we have the input to the input to the flop number 1. The output of the flop number 1 goes to the combinatorial circuits, and then the output of the combinatorial circuit is fed to the flop number 2, right? In this sequence of the data path, right, in this particular subsystem design, what we need to know is, what we need to take care is, the worst case condition. And in this particular sequence, if I have, let's say, only 2 flops, and then the clock skewing is given to us, then we can easily say that, okay, we can have a worst case where F1 is placed at a very far end of the clock, and F2 is placed, right, at the very near end of this flop, right? So the F2 is placed at the very near to the clock source generating circuit, and F1 is placed farthest to the clock source generating circuit, right? So in that sense, what we are saying is that although the clock signal is shown in this particular black lines, we can say that the F1 is actually getting the worst case, the skewed clock here, annotated with the dotted lines. And the flop number 2, because it is placed very close to the clock source generating circuit, it is getting the clock which is it is arriving very early, right? So the dotted lines, because it is skewed or because it is delayed, we can say that this particular clock is launching late for the first flip-flop, and then this particular black line is the clock which is arriving early for the second flop, right? So we are considering the worst case. If it is the other case, if it was the best case, we can say that, okay, F1 to be placed very near to the clock generating circuit, and F2 to be the farthest from the clock generating circuit, but then that will give you the best case, and then there's nothing to be worried about this combinatorial circuit design, right? But if it is the opposite case, that is where the worst case design comes in, and then we have to ensure that the combinatorial circuit design is designed in such a way that it still becomes resilient to the skewing, right? So if that is the worst case, so we have this kind of a skewing effect. So even if the D signal is made available just before the skewed, the T setup with respect to the skewed, if it is made available, we will have the Q1 generated with respect to the skewed, the transition, and then we will have the TPCQ, propagation clock to Q. Of course, this clock is nothing but the skewed one. So I will have the TPCQ, which is the characteristics of the flop design. So which is the output of the flop 1 goes to the combinatorial circuits, and then we will have the output of the combinatorial circuit after the propagation delay of the combinatorial circuits. And we have to ensure that that is made available just before the clock which is arriving early for the second flop. So it has to be made available T setup time before the clock that is being provided to the second flop. And in this case, the clock is arriving early. For the first flop, worst case condition, we are saying that the clock is delayed. It's arriving late, and in the second flop, it is arriving early for the worst case condition. Right. So in this particular case, right, the difference here is because of this skewness. In an ideal clock where I'm saying that all the clocks to the flip-flops are arriving at the same time, we will not have this skewness at all. Right. Whereas in this particular case where the clocks could be arriving at different particular time intervals for the flops, although it is coming from the same clock source generating circuit, because of the interconnect delay, there will be the skewness. And if it is a skewness, what should be my TPD, or what should be the maximum TPD, so that I don't have to, it still doesn't violate the setup time failures. Right. So looking at this particular timing diagram, we can easily say that, if I consider this T time period from this black line to this particular black edge transition, we know that this is TC, TC minus T skew should be greater than or equal to this TPCQ, TPD plus T setup. All right. So my TPD, the maximum TPD it could be, one could design for the combinatorial circuit is nothing but TC minus TCQ, T skew minus TPCQ minus of T setup. So this will be the sequencing overhead. All right. So the maximum delay constraints during the clock skewing condition is this one. Right. Remember that in an ideal clock where the clock arrival time is same for all the flops, this skewing effect will not be there. Now let's see how it, the clock skewing effect will have, how will it impact the minimum delay constraints. Right. So for the minimum delay constraints, because we don't know the placements of the flops, let's say I'm going to draw the flops, flop 1, and then we have the combinatorial circuit, and then we have the flop number 2. So this is the sequence in our subsystem design. Right. So, and then we say that, okay, it has a clock here, and then it has a clock here. This is the output, D1, Q1, combinatorial circuit output is D2, and then it gives the output of Q2. So this is the flow. In our previous data path system example, what we had taken was the clock is arriving, late here and early here. For the minimum delay constraint, it could be exactly the opposite way. It is the clock is arriving early for the flop 1 and it is arriving late for the flop 2, right? And in that case, because it's a worst case condition for the minimum delay constraints, we have to ensure that the combinatorial circuits TCD, the contamination delay, should still not violate the hold time failures, right? So if I have the clock here and then the dotted lines as the skewed clock, so I'm saying that the clock is arriving early for the first flop and clock is arriving late for the second flop, right? And what we really need to do is, even if it is a skewed one, we need to ensure that the F2 doesn't capture the signal, the contaminated signal in the first clock itself. So the F2 signal should actually capture in the second clock edge, and it should not capture in the dotted lines here, which is a clock which is actually skewed. It should get captured here in the dotted lines of the second clock, right? So what we need to do is that even if there is a contaminated output, we should ensure that it surpasses this hold time failure with respect to this skewed clock, right? So in that sense, if the D1 signal arrives early, before this particular clock for the flop 1, just before the T setup time, Then the Q1 can get get the contaminated output coming from the TCCQ of the flop 1 designs. And then the combinatorial circuit will pass the contaminated output after the contamination delay here. And we will have a TCD with respect to the Q1 signal, and then we have the D2 signal here, TCD. Now this D2 signal should arrive, it should make sure that the D2 signal arrives after the T hold time. The T hold time for the flop 2 is now with respect to the skewed clock. And the skewed clock is designed by this dotted lines, is given by this dotted line. So the T hold is with respect to this dotted line. So we need to ensure that the D2 signal arrives or surpasses after the T hold time for the flop T, so that it doesn't sneak in the first clock edge, of the skewed clock, but rather it should be made available in the second clock cycle of the for the flop 2 designs. Right, so looking at this particular timing diagram, we can easily say that the T hold plus T skew should be smaller than or equal to TCCQ and TCD. So my TCD, the minimum delay constraints should be, for designing the combinatorial circuit, is TCD should be greater than or equal to T hold plus T skew minus TCCQ. So remember that with the T clock skewing, this hold time effectively increases. Right, earlier if we are having the same ideal clock arrival time for all the flops, we did not have this T skewing parameter at all, and my TCD should be greater than or equal to T hold minus of TCCQ, which is much more easier to design. But now because of the addition of the clock skewing, the TCD value has a kind of further increased. Right, remember, for any kind of a combinatorial circuits, we have to ensure that it is characterized by the TPD parameters and TCD parameters. Right, in this case the TCD increases because of the T skewing, and then in the earlier slide we had seen that the TPD decreases. So the more and more this TCD and TPD comes closer, it becomes difficult, as a designer it becomes difficult to design the circuit. Right, if there is more margin here, TPD and TCD, it is much easier to design the combinatorial circuits. All right, moving on, let's take a look at the clock skewing effect for the latch designs. Right, so again here I'm directly giving the timing diagram for the latch design, but the latch design here, it is pretty similar to what we had seen. L1 going to the combinatorial circuit here, circuit number 1, and then that goes to the latch design L2, and then that goes to the combinatorial circuit number 2, and then that goes to the latch L3, and then so on. Right, so this L1, L3 and all are operating at the clock 1, phi 1 clock, and then L2, L4 and all the even number of latches are operating at phi 2 of the signal. Right, so here in this phi 1 of the signal, because it's a propagation delay, what we are saying is for L1 and L3 and L5 and so on, the clock is arriving late. So the clock is launching late for the first latch and arriving early for the second latch. Right, so that will be the worst case condition, which will ensure that the TPD value that we'll have to design for the combinatorial circuit 1 is actually, because there is the skewing factor, and it has to be slightly reduced. Right, so that is what we had seen for the flip-flop designs. But in this transparent latch, notice that the T skewing factor will be around 40 picoseconds, but the clock level being high, right, it will be available for almost around 482 or 500 picoseconds. All right, so the clock level being high, or the phi 2 clock level being high, will be around close to 500 picoseconds, whereas the clock skewing will be somewhere around 40 picoseconds. Right, so with this particular parameters, one can actually say that if the clock level high is around 500 picoseconds, and then even if there is a skewing effect, the D1 signal, although if it arrives during the clock level high, the skewing, which is around 1/10 of the 500 picoseconds, in fact less than 1/10 of the 500 picoseconds, it will not have that much of an effect. So even if the D1 signal arrives in between, after the late clock, Q1 will get easily captured. There won't be any effect here, whether the skewing is there or not. And then the D2 signal, the D2 will be nothing but the output of the combinatorial circuit number 1. So it produces after the TPD 1, and then the latch number 2 will give the output after the TPDQ of the latch number 2. And then the combinatorial circuit number 2 will throw the output after the TPD of the combinatorial circuit number 2. So in this case, because the T-skew is actually very, very minuscule in terms of the clock level being high, which is around 500 picoseconds, we can easily, in fact, the latch designs are really skew tolerant. So what, the skew, if the skewing is there, then also it will not have any effect. So the latches or the transparent latches designs are said to be skew tolerant. So even if the skew is there, it will not get reflected at the output. Right, so the maximum delay constraints doesn't have, especially for the transparent latches, it doesn't take into account the skewing effect. So hope this is clear, but it will have an effect in the minimum delay constraints, especially for the transparent latches. So even if I have a transparent latches in the same data path sequence of latch 1 followed by combinatorial circuit number 1 followed by latch number 2 followed by combinatorial circuit number 2 and then latch 3 and then so on. So then I will have this as a clock designed, and then for the minimum delay constraints, we will take the opposite as a worst case for, so the latch number 1, 3 and 5, we will say that the clock is arriving early, and latch number 2, 4 and 6, we will say that the clock is arriving late. So in that sense, I will have this skewed, the clock determining the output of the latch number 2, 4 and 6, all the even number of latches. Whereas the clock arriving early, we will consider it for the latch 1, 3, 5, all the odd number of latches, right? So this is what the clock is designed, and then the phi 2 clock will also have the similar the clock skewing circuit. So here is the clock skewed, which is arriving late, and then the clock arriving early. Clock arriving early is for the first, third, fifth, and so on. The clock arriving late is for second, 4 and 6 and then so on. So in that sense, if the D3 signal is available, then now D3 signal is going to the latch number 3. So I should consider this particular clock. So the output of Q3, the output of the latch number 3 with respect to this clock, it will produce after the CCQ3, which is contamination clock to Q3. And then the contaminated output then goes to the combinatorial circuit number 3. The output of that will be given to the latch number 4. So the D4 signal is the output of the combinatorial circuit number 3. And it is going to produce after the TCD time, the contaminated output. We need to ensure that this contaminated output, right, should surpass the first high level, or the delayed or the clock arriving late signal, and then the first level of the clock arriving late signal, and with respect to its t hold time, so that it will be captured in the skewed clock for the the high level of the phi 2 signal. So it will be captured in the second high level of the phi 2 signal. Although it is skewed, that is perfectly fine, but it should surpass the t skew and the high level of the phi 2 signal, clock signal, right? So in that sense, the clock skew is there, and then this t hold time is there. So what we need to do is this t non-overlap plus TCCQ3 plus TCD should be greater than this t skew and this t hold. So notice that this is what we have, t skew plus t hold, and then the t non-overlap plus TCCQ3 plus TCD should be greater than or equal to t skew plus t hold. All right. So the t skew plus t hold minus TCCQ3 plus t non-overlap is there on one side, and then TCD should be greater than or equal to this. So effectively what we are saying is the hold time effectively increases because of this skewing effect. Although this is the worst case. So what we are saying is we consider the worst case because we really don't know the placement of the flops. So we consider it to be a worst case because we know the characteristics of the flops. So if it is placed farthest, we know what is the t skew time. And we will utilize that to make sure that the combinatorial circuit that is placed in between the flops or in between the latches, it is still able to surpass the hold time failures.